Good day, everybody. Today we're going to use Lagrange multipliers to find an extreme value problem. It could be a context of a word problem. That'd be find the volume of the largest box that's contained in the first octant, and under this type of surface, x to the p over a to the p plus y to the p over b to the p plus c to the p over c to the p equals 1. Notice the intercepts in the first octant would be A00, 0, B0, and 00C. They all satisfy that. So those will be the intercepts. So for example, here's a plane, and if I want to find the largest box that can fit under the plane in the first octant, here's kind of a rough graph of the box. I plotted 3 of the sides. So something like that. Or if we consider an ellipsoid and then look at the first octant portion of the ellipsoid, then we get something like this. Again, here's the largest box that would fit in the first octant inside or under that part of the ellipsoid in the first octant. So notice one vertex is touching the surface, the other vertex would be at the origin. They were the diagonally opposite vertex. One last surface. And again, if we look at the first octant portion, which looks like this, the largest box that would fit under this surface, it looks like this. We've got the intercepts and so forth. So that's the idea. So these were our examples, but we're doing everything in general. So the volume is going to be length, width, height, but that will be given by x, y, z of the vertex that touches the surface. So essentially we want to minimize x times y times z, subject to being on the surface in the first octant. And so if we use Lagrange multipliers, then we've got to solve these 4 equations. F sub x is lambda g sub x, and if I take f sub x, I'll just get yz. If I take g sub x, I'll get p x to the p minus 1 divided by a to the p. And for how I'm going to solve it, I'll go ahead and look at what I'm going to do in the future. I'll multiply both sides of this equation by x, which now gives me back x to the p and xyz on the left. And similarly, if I do f sub y, that's xz, and g sub y times lambda, I'll get lambda times this, xz. Now multiply both sides of this equation by y, and so I'll get back lambda times p, and I'll get y to the p when I multiply this equation by y, both sides. And then lastly, f sub z is xy, g sub z is p z to the p minus 1 over c to the p. Again, I multiply both sides by z, so I get this. And again, I worked it ahead of time, so I know a good way to solve this problem. So here we get x, y, z all 3 times if we do that. And then, so if we add all 3 equations, I get 3xy on the left. And then I get lambda p times the sum of these 3 terms. But by the constraint, those 3 terms add up to 1. So 3xy is lambda times p. And I want to solve for lambda. So lambda is 3xyz divided by p. And now we're going to sub into the original 3 equations, which I have right here. So this yz equals lambda times this. So I'm going to replace the lambda on all 3 of these equations. So in the first one, I get yz is, there's the lambda, 3xyz over p, and then there's the p, x to the p minus 1 divided by a to the p. Now, I didn't write this down, but we're going to divide out yz. So y equals 0, z equals 0. We could consider for a solution, of course, those will give v equals 0, that one being the minimum. If you're in the first octant, you can't be negative for x, y, z, but you can be 0. Anyway, so we divide out yz, which would give us our minimum values, but we're interested in the maximum values. So on the left I have 1. If I divide out y, z, I now have x times x to the p minus 1. That'll give me x to the p. And then the p's cancel, so I have 3 over a to the p. And if you multiply by a to the p over 3, it's going to solve for x to the p. And then take the pth root, you get a over 3 to the 1 over p. And the same is going to happen for the other variables. Again, if I substitute in what lambda equals right here into here, then I get xz is, there's the lambda, this was the right, times p, y to the p minus 1 over b to the p. Again, I'll divide out the xz, so those could be zeros, but they lead to the min. P's cancel. We still have a y, so y times y to the p minus 1 gives me y to the p. And again, solving for y to the p, and then y, I get b over 3 to the 1 over p. And if we do it with the third equation, where we took the z partials, we had xy, and then there's the lambda, and then we had this for the g sub z. Divide out the xy from both sides. This z makes z to the p now, and solve for z, and you get c over 3 to the 1 over p. So those are that'll be the critical point. That'll lead to the max. Obviously, it's more than 0. One other thing we can note is that the values of x, y, and z for the coordinates of that vertex, or that lead to the maximum volume, are the coordinates that make it so that we're adding up 1/3 plus 1/3 plus 1/3. Right, so like z was c divided by 3 to the 1 over p. So what's z to the p? Well, I actually should look there. Z to the p was c to the p, and that'll cancel, divided by 3. And similarly, y to the p was b to the p divided by 3. And x to the p, well, it would end up being a to the p divided by 3. So the x, y, and z's are going to be so that you get 1/3 plus 1/3 plus 1/3. No matter what the surface was. And then for your volume, if you want to know what that is, well, if you multiply the x, y, and z's, we get ABC divided by 3 to the 3 over p, or ABC divided by 27 to the 1 over p, or ABC pth root of 27. And again, that'll be the maximum. The minimum volume occurs at these intercepts. So that's the result. Hope you enjoyed that and learned something. So have a good day.